This is the first video in AP Calculus on section 6.4 in our textbook, which is on exponential growth and decay. And so this actually is going to go back and review a lot of the exponential stuff that you, or hopefully that you learned back in accelerated geometry or in Algebra 2 when you first learned about exponential functions. So the law of exponential change basically says that if your y value changes at a rate proportional to the amount present, so that would be where the rate of change of y, dy dt, is equal to a constant k times the current y value. And so if y is y sub 0 when time is initially 0, then your basic exponential growth function or exponential model function is y equals y sub 0 e to the kt. K is either the growth constant if it's greater than 0, or it's the decay constant if it's less than 0. So, for example, y equals 2e to the 5t would be an example of an exponential growth function, whereas y equals 2e to the 1/2 t would be an exponential decay function because our rate of change is less, not about negative 1/2, because our rate of change is less than 0. One of the most common uses of exponential growth is with money in a bank where it is earning interest, and so a compound interest formula, which sometimes looks like that y equals y sub 0 e to the kt. You may remember PERT, perhaps, from when you were first studying exponential functions. So P stood for the principal amount, or the initial y value, and then R was your interest rate as a decimal, and then T was the amount of time in years that you were leaving it in the bank. But if it's not compounded continuously, so PERT is for continuously compounded interest, but if it's not compounded continuously, then you can use this A of T formula, where it's A sub 0 times 1 plus R divided by K to the KT, where K represents the number of times over the course of a year that interest will be calculated. So whether it's monthly or every 6 months or quarterly or daily or whatever, then the formula would look like that. But for this particular example that we're doing here, example 1, we want to complete the chart for continuously compounded interest. So we would actually use the PERT formula. So if our initial investment is $5,000 and our interest rate is 5% or 0.05, written as a decimal, then we want to find two things: the time that it would take for that amount of money to double, and the amount of money that we would have in the bank after 10 years. So if we're thinking about time to double, then that means our final amount would be double our initial amount, which was $5,000, at an interest rate of 0.05. So then we just need to solve that for t. So we would begin by dividing the 5,000 over. So then you get 2 equals e to the 0.05 t. Now we need to undo the e. So ln on both sides will eliminate that e. So now you get the natural log of 2 is equal to 0.05 times t. Don't find the decimal for the natural log of 2. We'll wait until the very end of the problem to find the decimal values. So t is then equal to the natural log of 2 divided by 0.05. And since you're not going to go tell somebody that it's going to take them natural log of 2 divided by 0.05 years for their money to double, you would then put that in the calculator, and you should get 13.863 years. And we do still want to go to 3 decimal places. So then the amount after 10 years, we don't know what the amount is. We know we're starting with $5,000 at an interest rate of 0.05, and the time is 10. That one's much easier because you simply just implement that right into your calculator, and you should get $8,243.61, which makes sense that it should be less than 10,000 because we know it's going to take us over 13 years to reach $10,000. So 10 years should be somewhat less than $10,000. So all of that you could have done several years ago when you were first learning about exponential functions. So how do differential equations kind of come into play with exponential functions? Well, if instead of being added at discrete intervals of time, if the interest is added continuously, like in the problem we just looked at a rate proportional to the amount in the account, which is where your interest rate comes from, we can model the growth of the account with an initial value problem instead. So the differential, because it's proportional, this goes back to what we were saying at the very beginning about the law of exponential change. The rate of change of our y value, so in this case of the amount in the bank, with respect to time is equal to our interest rate times the amount of money at that current time in the bank. So dA dt equals RA, with the initial condition that a of 0 is called a sub 0. So the amount of money in the account after t years, if we then wanted to find that, we could solve this differential equation here at the top of the screen. We would have dA dt equals RA. But if we're wanting to solve it, our two variables are A and T. R is a constant amount, so it's not considered a variable, it's considered a constant. So if we wanted to solve this differential equation, we would have to first separate the variables, which would mean that the dt would have to come over here to the right, and the A would actually have to divide over to the left. The R could stay put where it is over on the right-hand side. So now that we've separated the variables, we can integrate this. Over here on the left, this is essentially 1 over A times dA. So 1 over A would integrate back to the natural log of the absolute value of A. And then on the right-hand side, R is a constant, but we're integrating with respect to T. So that would become RT. And then we always have plus some sort of constant. Now, if we want an equation for the amount of money, we want this equation to say A equals amount of money equals. So I now need to solve this equation to get the A by itself, which would mean getting rid of the ln. So remember, we can put an E in to do that. And when we do that, the absolute value goes away. We have E to the RT plus C. Over here to the side, hopefully you remember this from separation of variables. Saying E to the RT plus C is the same as saying E to the RT times E to the C. But E to the C is a constant being raised to another constant. So that's still just a constant. So we can write it as a constant times E to the RT. The interesting thing is that that constant, if we were to actually substitute in time 0 and A sub 0, the constant is the initial amount. So A equals A sub 0 times E to the RT. So there you go. That is our exponential growth model that we've been using. It just, the initial one had Y and Y sub 0 in it, and K's. This has A sub 0, and R. But this is the logic of where that whole relationship came from, is from differential equations from the very beginning. So let's look at another exponential model. It says, suppose you have P dollars invested in an account at an interest rate of 5.6% per year, compounded continuously. This means that at any given instant, the amount Y in the account is increasing at a rate of 5.6% of the current balance. If T is the time since the account was opened, first thing they want us to find is the differential equation that models this situation. This sentence right here is our differential equation. That at any given instant, the amount Y in the account is increasing at a rate. So dy dt as increasing at a rate of 5.6% of the current balance. So there's your differential equation. The increasing rate is dy dt, 5.6% is our interest rate, and then the current balance would be represented as y. So that's our differential equation right there. Or you could, instead of calling those y's, actually it should be p's. Now let's change that real quick for less confusion down the road. Those would be P. All right, so then B says suppose $100 is the initial amount invested in the account. Find a formula for the amount in the account at any time t. So this is like an initial condition situation now. So I have a differential equation, dp dt equals 0.056 p. And I'm going to solve that with the initial condition that at time 0, the value of p is $100. So I'm going to need to separate my variables so that I can solve this differential equation. So very similar to the one we just did with the a's, the p is going to divide over here, and the dt is going to multiply over here. Then we're going to integrate both sides. We get the natural log of the absolute value of p is equal to 0.056 t plus c. Insert an e on both sides, and you get p equals, now I know the e to the c, that's going to be a constant, times e to the 0.056 t. Now I want to actually find the value of that constant, so p is $100 when time is 0. So this over here becomes e to the 0, which is 1, so my constant is 100. So that means that my general formula to find the balance at any given time is p equals 100 times e to the 0.56 t. So then they could ask, find the dollar amount at such and such a time. You could do any of that using that stuff right there. All right, so that wraps up the first video. I'm going to continue to make other videos to go over some other exponential growth and decay problems.